Okay, so let's study Newton's method for linear regression example. So in many cases, we use first-order gradient descent method to solve linear regression, but in some cases, we can use higher-order methods like Newton's method for better result. But if you want to solve very large system, well, maybe you can consider deep learning with big data. Then, well, it's very difficult to solve, difficult to find a good solution with second order or higher order methods because, well, the higher order methods require much more memory. So it's not feasible in many cases. But for smaller problems, maybe you can split one big problem into many small problems. Then you can apply higher order methods repeatedly. Well, this is the strategy used for some reinforcement learning problems. Okay, so I think it's good to introduce Newton's method here. Okay, so we have linear hypothesis here for linear regression problem. So y is ax plus b. So in this case, the input is x and output is y, and we want to find ax and a and b. They are a and b are trainable coefficients. So you may consider the trainable weights in neural network. Well, if this is a neural network, this is a very simple one. Well, this is actually just one neuron, but you can apply the same method, the same higher order method for deep neural networks. So you want to find good or best. Well, we want best, but well, sometimes we need to satisfy just good solutions. And anyway, we want to find good A and B, the trainable weight, the values of trainable weights to satisfy the constraints below. So in this example, we want to find good A and B for these constraints. There are two constraints. First one is x0. When x0 is equal to 0, we want this linear hypothesis outputs number 1. This is the first constraint. And for the second constraint is 0.5, 0.5. So if you input 1.5 to this function, then we want it to return output 1.5. Okay. So you can define a mean squared error function to define how wrong your linear hypothesis from your constraint here. So for each constraint, you can define error function like this. So we have two constraints. So we can use y0 here, y0, and x0, x0, and error 0. They also define error 0, e0. And you can also define E1, Y1 by introducing Y1 and X1. Okay, so we have two equations here. And well, for all constraints, we can add two error functions, E0 and E1, to obtain error function. So in this case, I is 0 and 1. Okay, let's think about gradient descent method. So we want to find a set of A and B which minimizes error function E, right? So a popular gradient descent method in deep learning community uses the method like this. There is a typo here. This should be minus number or negative eta. So let's go to let's just skip to this part. So we define the error function as a summation of two error functions. So we can also compute round E, round A, the gradient of error function with respect to coefficient A by adding the gradient defined by each constraint like this. And here, one more time, this. Okay, let's do this. The gradient descent method is very popular, but tweaking eta, I mean here the learning rate coefficient. So we need to try several times to find a good learning rate number for best performance. Well, it requires human work instead of computer work. So in some cases, we can use second-order derivatives to overcome this problem. Okay. So the mean squared error E can be approximated by the second-order Taylor series like this. So far, we used only the first-order gradient of error function E with respect to the trainable coefficient A and B. The gradient. So in this case, we can use the second-order Taylor series. Okay, so we can define error function as a function of A, the trainable variables, trainable coefficients A and B. So in this case, we can define. We would like to find the second. Actually, this is the first order. Second order Taylor series of E here. So A delta X, A plus delta A, B plus delta B. So this is EI A B plus. This is gradient. What was that? The gradient of matrix. So gradient E is the gradient of matrix. So round E over round A, round E over round B. This is it. And delta A, delta B. This is a column matrix of delta A and delta B plus 1/2 delta A, delta B, and there is one more matrix H here, delta A, delta B. So this is the second order Taylor series of approximation of your error function to find good variables A and B. Okay. And we introduced a Hessian function, which includes second order derivatives of error function. So far, we used only first order derivatives, well, round E over round A or round E over round B. In this case, round squared E over round A squared, right? Round squared E, round A, round B. And well, this is a symmetric matrix. So we want to find delta A and delta B. What we need is delta A and delta B so that we can find A plus delta A and B plus delta B, well, which minimize E. That's what we want. So it requires the inverse of H matrix. Okay, since we want A and B which satisfy this condition, this is the equation from the previous slide. Okay, and well, we want a condition like this. So gradient E plus H delta A delta B equal to 0. So I told you that we want to find this one, delta A and delta B. right? A plus delta A is the proper coefficient we want to obtain, and B plus delta B is the B we want. Okay, so move this one to the right side and use the inverse matrix of this Hessian matrix. Then we can obtain delta A and delta B in an each way. Right? This looks clear. And we can obtain second order partial derivatives of E as follows this way. So let's go to here. So y minus ax minus b squared, right? So we can obtain the round squared E over round x, and round squared E over round y, and round squared E over round a round b, yeah, from this equation. And yeah, you can do this. Okay, so here is a numerical example. So okay, let's go back to here. So we want to delta x 0, 1, delta x1, 0, 1.5, 1.5. So let's go back to the slide here. Okay, so in this case, Hessian I would like to use some pencils, but okay. So H is 1, 1, 1, 2. Then the inverse matrix of H is 2, minus 1, minus 1. Well, we can use some library, external library, to calculate this one. And for gradient E, let's go to here. So this is round E, round A, round E, round B. Okay, so we can calculate it when A0 is 0 and B0 is 0. This is the initial condition of this method. And don't forget that the error function is, in our example, we introduced two constraints, and well, so delta A, delta B minus H minus 1 AB is 0.51. So the initial condition was A0 was 0 and B0 was B. So A 0 plus delta A, 0.5 is 0.5, and 0.0 plus 0 plus 1 delta B, 1 is 1. So our answer is y is equal to y is 0.5x plus b, and this satisfies our constraints perfectly. Okay. So we did the same problem. We solved the same problem using the gradient method iteratively. We repeatedly applied the gradient of error function with respect to A and B. But in this case, we can directly compute the answer in one step. Okay, so this is an example of the Newton's method for linear regression.